Imagine for a moment an ice age greenhouse gas that could suddenly blast its way out of the ocean floor and, well, reshape our planet's climate in what amounts to a geological blink. Deep beneath the frozen waters off the Siberian coast, a team of scientists is about to find out exactly what happens when the planet's thermostat finally breaks one of its most dangerous, delicate seals. We're talking about methane clathrates, a strange, icy substance that, honestly, holds the key to a true global catastrophe. So stay with us to see what one small tremor on the seafloor could unleash, why it's such a terrifying threat to all life in the ocean, and what these desperate researchers tried to do to stop a chemical reaction that's, already underway. What are these icy cages, and just how much is really down there? The deep ocean floor, especially along continental shelves like those in the Arctic, is home to one of the planet's biggest secrets. It's called methane clathrate, or sometimes folks just call it methane ice. Think of it, if you will, like a giant unstable ice cube where cold water molecules have built a tight cage around a molecule of methane gas. This methane is the same natural gas we burn for energy, but here, it's packed solid. For millennia, this ice has stayed stable because of two simple things: intense pressure from the deep water column above it, and freezing cold temperatures. It's estimated that the amount of carbon trapped in these clathrates, globally, could be, believe it or not, twice the carbon found in all the world's proven oil, coal, and gas reserves combined. It is a vast, frozen energy source, held by the slimmest of margins. But methane, once freed, is a nightmare. It is over 80 times more powerful at trapping heat in the atmosphere than carbon dioxide over a 20-year period. This icy prison is the Earth's greatest single reserve of potential greenhouse gas, and it's stable only as long as the pressure stays high and the temperature stays low. If the clathrates are so deep and cold, what could possibly start the melting process? Our story focuses on a highly specialized team of physical oceanographers and geophysicists operating near the Laptov Sea, off the coast of Siberia. They weren't looking for a disaster, honestly. They were just monitoring a large known clathrate deposit. Using a heavily instrumented deep-sea submersible, they were taking samples and measuring the ocean's properties right above the sediment. Their routine work became terrifying when their seismographs started reporting small, distinct tremors. Not huge earthquakes, but subtle, repeated shaking. The area had been mapped with a known, but dormant, fault line. The assumption was that this fault was stable. But the new readings told a different story. One of the team's ocean sensors showed a slight but alarming spike in the temperature of the bottom water, a rise of less than 1 degree Celsius. But this small temperature change, combined with the pressure fluctuations from the seismic activity, was enough to push the delicate balance of the methane ice over the edge. It was the pressure, not just the temperature, that was the key. The team had found their nightmare scenario. The seismic jostling was causing a localized hotspot and an instant pressure drop, triggering a phase change. The solid methane ice was turning straight into gas. In the submersible's lights, the crew suddenly saw what looked like a blizzard rising from the seafloor, a plume of pure methane bubbles, rushing upwards from a fracture in the sediment. The Clathrate gun was beginning to fire. Why is this sudden, massive bubble plume more terrifying than a slow release? And what exactly is the Clathrate gun? The Clathrate Gun Hypothesis is a scientific theory that proposes massive, rapid destabilization events have actually happened before in Earth's history. This means that if enough methane is released quickly, it could trigger a runaway feedback loop. Here's how it works. First, a warm ocean releases methane. Then, methane hits the atmosphere and traps massive heat. The atmosphere gets warmer, which makes the ocean warmer. That warmer ocean melts more clathrate, and this in turn speeds up the release, causing a huge, unstoppable warming spike. The team knew that if the small leak they saw widened into a full-scale reservoir release, the atmospheric consequences would be devastating. It would be a warming event so rapid it could be compared to minor extinction events in the deep past, changing global weather patterns and sea levels almost instantly. Their core mission shifted from observation to emergency intervention. The plan was desperate. The team had a small stockpile of experimental pressure equalizing devices. These were basically high-tech injectors meant to pump a supercooled brine solution directly into the seismically active fault line. The goal was to restore the stability zone by lowering the local temperature and increasing the localized pressure, just enough to seal the fractures and force the rising gas to turn back into stable ice. It was a race against the clock, with a gas plume that was already hundreds of feet high, heading for the surface. But what if the greatest danger wasn't what the gas did to the air, but what it did to the ocean? The scientists were focused on the terrifying global warming threat, but the deep ocean environment held a secret they hadn't fully prepared for. They assumed the methane would just bubble up and be gone. They were wrong. As the massive plume of methane gas rushed upward, it became a massive feast for tiny, unseen organisms, methane-eating microbes. These microbes live in the water column and are perfectly designed to consume methane. The instant this immense new food source arrived, their populations exploded. The chemical process these microbes use to break down methane is called aerobic oxidation, and it requires one crucial thing: oxygen. They begin consuming dissolved oxygen in the surrounding seawater at an incredible rate. The results were instant and localized. The team's oxygen sensors in the water column right next to the plume plummeted. They weren't just seeing a methane release, they were watching the formation of an instant hypoxic zone. Hypoxia means extremely low oxygen levels. This massive bloom of methane-consuming microbes was rapidly sucking the life out of the water. Marine life, from tiny plankton to large fish that rely on oxygenated water, would be instantly suffocated. The atmospheric threat was global and slow, but the oceanic threat was local and immediate. Before the methane could even warm the atmosphere, it was triggering a massive, rapid, oceanic die-off in the deep, silent darkness. The submersible pilots fought the currents, deploying their cooling probes near the unstable fault. They pumped the cold brine, watching the temperature gauges anxiously. For a brief moment the plume seemed to slow, the bubble stream thinning as the cold liquid hit the fissure and compressed the gas. The numbers stabilized. But then, a secondary sensor, located further up the fault line, registered an even sharper pressure drop. The initial release had simply moved the stress, opening a new, larger pathway. The plume they were trying to stop was just a warning shot. The methane-consuming microbes, now multiplying beyond control, had created a lifeless void thousands of feet deep. The pilot's final log entry, before the power cut due to system overload, recorded the oxygen levels hitting zero in the surrounding water. The deep ocean environment was far more interconnected and far more fragile than anyone on the surface had dared to imagine. The release wasn't stopped, it was simply moved. The team's last sight was the original plume now joining a massive, turbulent second stream, a twin column of methane rushing toward the surface, a chemical reaction that would now run its course, regardless of anything done at the bottom. The warming might be years away, but the death of the deep was happening right now. The ice melted, the gas rose, and the world above wouldn't know what was truly lost until the silence of the deep reached the surface. It's a chilling thought, isn't it? That a single invisible chemical reaction in the deep ocean could have such a devastating impact on our planet's climate and its ecosystems. If this script kept you on the edge of your seat, give this video a like. It really helps the channel share more stories about the hidden forces shaping our world. Subscribe and turn on notifications so you don't miss our next video, and tell us in the comments, what other deep-sea mysteries scare you the most?
Yeah.